k. Okay, this now, this period equals 2 pi times square root of m over k. That now is the equation on page 330, equation 10.11. I also derived for you what the frequency is. The frequency is just 1 over this period, which is this. So this is what I've just demonstrated here. It's much longer and much more elaborate proof using calculus and using differential equations. But this really is a standard way in physics of deriving what the period is for oscillatory motion and what the frequency is. Frequency and the period is just are actually, the period is simply the reciprocal of the frequency and vice versa. Okay, so again, let's review exactly what this means. If we could calculate what the spring constant is, that's this, every spring has a certain spring constant, that's what K is. Remember, the units of that are Newton per meter. Okay, then I attach a mass to this. In this case, I'm just going to let the mass of the spring be what the mass is. And if I elongate it a certain bit, it oscillates at a certain frequency, so many cycles per second, or the reciprocal of that is t, so many seconds per cycle, like 1, 2, this is maybe about 1 cycle per second, or a period of about maybe 1 second. Okay, so this is how this equation works. I hope this derivation here is understandable, and that's all of that kind of fancy derivation I'm going to do, at least for right now. If you have any questions about it, you can talk with me. That equation is something you will need to know, and the period equation, we will definitely use it for solving different types of problems. Okay. Now, if we continue onward, let's flip on. There's some example problems you can do using that equation on page 332, which I'll let you do on your own. Okay, flip on to page 333, and there's one more very important concept that this chapter talks about. Actually, two more concepts that this chapter talks about, and that's start on page 333, the potential energy of a mass spring system. Okay, if you look on page 334 and 335, okay, if I have a spring system, okay, and I elongate this spring, a certain mass to it, and I elongate this spring by a certain amount. Here's a spring constant. It takes a certain amount of energy to pull this down, okay, or to push it up, or vice versa. And that energy, if I pull down a spring, there's a certain energy. Here's the spring under equilibrium conditions. If I pull the spring down a certain distance, there's a certain amount of energy locked into that system. And why do we know? Because if I let it go, it starts to oscillate, and it starts to move at a certain velocity. And so there's a certain amount of energy that's in this spring system. And this potential energy, it hasn't been released yet. But then when I release that energy, and it goes from potential energy into kinetic energy. Okay, does that make sense? Now notice what we have, the oscillatory motion of the spring changes at the equilibrium position. There's no potential energy of the spring. If I could stop this from oscillating. There's no potential energy of the spring. But if I pull it down, I have put energy into the spring. Then when I let it go, it starts to oscillate. And notice, study the motion. When it's all the way down here, when the spring is all the way at its furthest elongation, it's all the energies in the spring energy. When it comes through the equilibrium position, it's traveling at its fastest. It's all in kinetic energy. When it compresses a spring, it takes that energy and puts it back into spring energy, potential energy of the spring, which then the restoring force pushes it back down, and it's moving through kinetic energy. And so what we have is a transfer of energy from kinetic to potential to kinetic to potential, back and forth as the spring oscillates. So when the spring oscillates, there is a natural conversion from potential energy to kinetic, and back and forth and back and forth. Okay, so the book, if you look on page 535, the book gives an equation for what the potential energy of a spring is. What we're going to do is we're going to derive that. Now, it uses a little bit of calculus, but I think you can do this. Remember what the equation for work is. Work, whoops, I think maybe I need a new pen, excuse me. Let's see if this pen works any better. Ah, yes. Work or energy is defined as a force operating over a certain distance. Okay? So, in this case, what I want to do is when I pull this down, I want to see how much energy how much energy was necessary to pull this spring from here, equilibrium position. This is the equilibrium position, down to delta x. It took a certain amount of energy, and that's the energy that's locked into the spring system as potential energy. Now, when I pull the spring down a certain delta x, that gives a certain amount that increments the energy up a certain amount. Okay? Now hopefully this makes sense. If I let delta x be a real little differential, I would say a little differential x times the force gives me a little bit of work done. Okay? Again, d just means differential. A little bit of displacement here times the force gives me a little bit of work done. Differential amount of work. Now what is the now the total work done from here down to here, the total work done is simply W, and that's simply the sum of all these little delta W's. Or, to use calculus, it's the integral of all the little dW's, and all the little dW's are, again, if I use the summation sign, it's a summation sign of the force times delta x. Using the integral sign, it's the integral, I integrate the force times dx. Now what is the force? The force that has to be overcome is the restoring force of the spring that acts in the opposite direction. Okay? Okay? So, this now, so the force we're talking about is the force of the spring constant times x. Now, for right now, I'm just going to leave off the negative sign because the negative sign just means that the restoring force acts opposite the direction of the x. It's just a sign convention. So I'm going to go ahead and embed this into here, and what I get is that the work is equal to the integral of kx times dx. Kx is simply the restoring force. That's the restoring force times dx. Dx just like delta x. Okay? Now, and I'm going to integrate this from 0 to a certain, we'll call it a certain x that we'll just call it x. Hope that's clear. We'll call it x1 just to make it simple. Give it a certain x1. Okay. When I integrate this, the k as a constant comes outside the integral, and I get the integral of x dx. And if you know how to integrate this, it would be k times 1/2 x squared, evaluated from 0 to a certain x1, or it's simply 1/2 k x1 squared. Okay, so in general, what this means is this. If I elongate a spring from 0 down to a certain x distance, okay, the work that's necessary for me to do to pull that down is equal to the work's necessary to pull that down is 1/2 times k times x squared. Okay, we just derived this. K, again, is a spring constant. X is simply the distance that I pull it down. So, if I pull it down a certain distance, what that also means is that the potential energy that's locked into the spring is this amount, is 1/2 kx squared. Now, what's the units for energy? This is joules. Joules of energy. Think back to chapter 8 where we talked about potential energy and kinetic energy. This is exactly the same concept. Okay? So imagine we have a system, a spring system, where we elongate the mass down a certain distance. Here's our equilibrium position. We elongate it down to x. This is our x distance. So how much energy do we have locked into the system? At this point, the energy is, the potential energy is 1/2 times k times x squared. Okay. Now if we let that go, the mass starts to move back up. Now what is the potential energy at this point right here? The potential energy at this point where x equals 0. Well, potential energy is 0. We put a 0 in here, 1/2 k times 0 squared is 0. Potential energy is 0. So what happened to all the energy? Well, the energy went into kinetic energy. There, at this exact point where the mass is flying back up, there's no potential energy, but there certainly is a lot of kinetic energy. It's transferred into kinetic energy. What's the formula for kinetic energy? 1/2 mv squared, where m is the mass, this mass that we have on the end of the spring, and v would be the velocity that the mass is traveling at right at the point where it goes through the equilibrium position. Okay? Then, when the spring is compressed again, what will happen? The mass is pulled down, it flies up, it goes through here, but it continues on until it gets to this point here, where the spring is really compressed. And at this point, Notice at this point, when it gets up to this point, the potential energy here is again 1/2 kx squared, assuming we have no loss of energy, where this distance is x again up to this point, but it's on the opposite side, but the mass slows up, finally gets to this point and it stops, and the kinetic energy is 0. There is no velocity. At this point we have kinetic energy, but it's on the opposite side of the equilibrium. The spring is compressed. The spring is compressed a lot. It pushes back down. The spring elongates, pushes through here, through the equilibrium point. There's no potential energy, but all the energy is now in kinetic energy. So the mass keeps on moving, and it slows up, finally gets to here, this point again, back to its starting point, where now all the energy is in potential energy, and the kinetic energy is 0 because the velocity is 0. So you see how this oscillatory motion works. When a spring oscillates back and forth, we are transferring energy from potential energy to kinetic energy, back to potential, back to kinetic, and somewhere in the middle, like at this point right here, what is the total energy? Notice that in this case, the total energy is always equal to the sum of the potential energy plus the kinetic energy at any one point. Well, that must be equal to the potential energy at x equals the amplitude. Okay? So what we might say is that if we call this the A, if we let x equal A, the amplitude at this point, and x equal A at this point, okay? In fact, what we can say is that this is plus A and this is minus A, and this is our x-axis, where this is minus side and that's the plus side. A is amplitude, that's the furthest distance that the mass travels, that the total energy is 1/2 k A squared. That's the total energy. Okay? Now that's the energy it has at everywhere throughout here. When the mass is at the extremes, all the energy is in potential. When the mass is in the middle, all the energy is in kinetic energy, and potential energy is 0. But when it's somewhere here in the middle, there's some amount of potential energy, and there's some amount of kinetic energy, and it's a mixture. Okay, so I hope this makes sense. And if so, that the energy is when it's oscillating is completely transferred back and forth from potential to kinetic and back and forth. Okay, so for instance, we could calculate at this point if we wanted to, suppose one of the problems was to calculate what the velocity was right at this point here. How would you do it? Well, we would simply say that we know what the total energy is. The total energy of the system is 1/2 k A squared. That's the total potential energy at the amplitude. But at the equilibrium point, all that energy is transferred to 1/2 mv squared, to the velocity. So we could say, let's calculate the velocity. We cancel the halves. Okay, now I'm going to divide by m, k over m, a squared equals v squared. I take the square root of both sides, and I get v equals square root of k over m times a. So that would be an equation using algebra of the velocity right at the equilibrium point. And is based on the spring constant and the mass and also the amplitude. Notice the higher the amplitude, the greater the velocity. So it makes sense. Okay. All right. There's one more thing that we have that comes under this chapter that we have to talk about, and that is a pendulum, like a grandfather's clock. This has the pendulum is something that is a real common thing that we see, and it oscillates back and forth, or it has periodic motion. If you look on page 338, this is a pendulum. Normally a pendulum just simply hangs down. There's a certain weight to it. There's a certain mass to it. And suppose this is a string here. Doesn't have to be a string here. It could be a string, or it could be a rod, like if you have a grandfather's clock like this, and you have a pendulum going back and forth like this. Now if I pull this at a certain angle here, and then I let it go, what's going to happen? This right here is a pivot point. This point stays stationary. What's going to happen? Gravity is going to pull this down, and this is going to oscillate back and forth. It's going to oscillate back and forth, and over here it's going to come over here, and it's going to oscillate back and forth. And the period of motion from here back to here, that's one period, and it's so many seconds per cycle. Okay, that would be the period. The frequency, obviously, is 1 over the period, and that's X number of cycles per second. Okay. Now, I'm not going to derive this, but there's an equation that's right on page 341, and it goes that the period of motion for a pendulum is equal to 2 pi times the square root of L over G. This length, the arm length here, has a certain length to it, L, and G is the gravitational traction, 9.8 meters per second squared, and L is the length of the arm, length of the pendulum arm. So if you look at this, this makes sense. The longer you make the arm, the longer the period, the longer it takes this thing to oscillate back and forth. So it makes sense. Now if you look at page 340, it has some good notes there, and what it talks about is the fact that this actually is only approximate. I hate to tell you this, but it's only approximate, and is basically good for more or less when this angle is relatively small. Okay, what do I mean by that? Well, the book talks about the idea that for about maybe less than 20 degrees, okay, that this is good for. Well, actually, the smaller you make the angle, the better this equation is. Now we could, remember how we derived the other equation for the period and the frequency of a spring? We could go through the exact same kinds of physics, sinusoidal motion, to come up with the equation for the period of a pendulum. We're not going to do it because we're running out of time. But the concept is very much the same. That is, if we have, let me just draw you out a little bit of how you would do it. You have I'll just kind of get you started. Some of you might be able to do this on your own for fun. But you have a certain mass here at a certain angle. Okay. Now, what is going to pull this mass back down to the, again, this is the equilibrium position, right? What's going to pull this mass to the equilibrium position? Well, it's obviously gravity. Gravity acts down, right? Gravity acts down. Now, why doesn't the mass just fall straight down? Well, it can't. Why can't it? Because it's restrained. This is a restrained problem where the mass is only capable of moving in an arc. Okay, now remember the arc equation, S, and this is R, if I call this R, remember the equation S equals R theta. They even talk about that on page 240. Okay, S equal R theta, or in this case, R is L, the length. This will be L. Okay, so the mass is restrained to move only along here. So even though the weight acts down, only a certain component of the weight is actually involved in this. If the weight moved straight down, then we say all the force, all the weight acts on the mass in moving the mass, but actually in this case, not all of it does. So it's only the force that's going in this certain direction that is responsible for what we might call the restoring force. So, well, that's all I'm going to go. If you want to, it would be a fun problem to try to derive the similar equations like we did before. I'm not going to do it, but suffice it to say that this is the equation that we're going to use. And when it comes to the lab, actually we're going to do a lab on some pendulums, and we're going to come up, I'm going to, in the lab, give a more exact formula for how you can calculate this when thetas are larger than just small angles. Well, I hope this is a good overview of Chapter 10. In the next video clip, we'll go over the review questions and the problems, and also do an overview of the lab for Chapter 10. Thanks. God bless you.